Welcome to the 10.5 notes for Math 127. We're going to be looking at something called the binomial theorem. And as part of that, we're going to be looking at a really, truly beautiful triangle called Pascal's triangle. And I wish we had more time to talk about Pascal's triangle because there's pretty awesome stuff in there. And I hope you get to explore some of that in another class, or maybe you'll explore that on your own time a bit. But we're going to look at this through the expansion, through the lens of the binomial theorem and expanding out binomials taken to various powers. So before we do that, we need a little bit of background information. The first is the idea of a combination. So if you think about something like a combination lock, imagine you had 10 numbers to choose from to pick a combination for a lock, and you could pick 4 of them. How many different ways could you put in that combination if the order of the numbers didn't matter? So like maybe you chose the code 1, 2, 3, and 4, and it didn't matter what order you entered in those 4 digits as long as you had them. That is called a combination when you think of how many different ways could you pick 4 out of 10 numbers. So there's a couple different pieces of notation that we could use for writing the combinations. The first looks like this, where n is the total number. Sorry, see if I can get a color here that works. N is the total number of items you're picking from, and R is the number of items that are being selected. So if I had, like, again, 10 numbers to choose from, and I'm picking some combination where I pick 4 numbers, and this would be, doesn't matter the order in which those 4 numbers are written. Another way we could write this is we could write this like this, where we have 10 items and we're picking 4 of them. And if we wanted to actually calculate what that would be, we would, on the top, we would write a fraction with 10 factorial. And on the bottom, we would write r factorial, r being the 4, and then times 10 minus 4, which is 6 factorial. And we could calculate that and see what that value actually is. And the nice thing is, of course, 10 factorial could be written out as 10 times 9 times 8 times 7 times 6 factorial. That 6 factorial would cancel out on the denominator. And then 4 factorial is 4 times 3 times 2 times 1, which is a little bit easier to calculate out because we have 4 times 2 is really 8, which divides out with that one. 9 divides by 3 to 3, and we end up with 10 times 3 times 7, which is 30 times 7, or 210. Now, there's also a way to calculate this on your calculator. You don't actually have to memorize this formula at all. It'll do it for you. So let me show you how to do that. If I did want to do, for example, 10 combination 4 or 10 combination 4 in either notation, what you would do first is you would type the number 10. And then you would go in your calculator to math. You want to arrow over to probability. And then you pick the third option, which is the option for a combination. And then you would say, out of the 10 numbers, I'm selecting 4 of them. And I would get that same 210. So again, the way we would enter that into the calculator is first you would type whatever number is in the n position. And then you would do math, probability, and option 3. And last, you would type the number in the R position. So let's just try this a couple more times, starting with 6 combination 4. First, I type the 6, and then I would go math, probability, option 3, and I want 6 combination 4, which is 15. And I could use the formula. I could have done 6 factorial over 4 factorial times 2 factorial, and by the time I reduced it all down, I would have gotten 15. But we have the calculator available for us, so you can do it that way. So pause the video, try 6 combination 0 and 8 combination 2. When you're done with that, restart that. All right, the answers are up there on the screen. By the way, 6 combination 0 equals 1, because if you have 6 items and you're not picking any of them, there's only one way for that to happen. But if you have 8 items and you're picking 2 of them, there's 28 different ways you could select items. So on the calculator, again, you would type n, and then math, probability, 3, and then type whatever number is in the R position, which would be the smaller of the 2 numbers. this might feel unrelated, but it is related. We're going to look at something called Pascal's triangle. And you might remember way back at the very beginning of this unit, we talked about a Fibonacci sequence. And the Fibonacci sequence looked like this: 1, 1, 2, 3, 5, 8, 13, 21, and so forth. Well, let's say we take those same numbers and in that sequence, we put it in a triangle where we start with a 1 here. And then let's say all the way down the triangle, in fact, all the way down the diagonal, we put in 1s. And then we do that same type of adding to get any empty space. I'm going to add the 1s above. 1 plus 1 would make this a 2. And then if I want to find this space, I'll add the 2 little honeycombs above it. 1 plus 2 is 3. Same thing here. I'm just adding the 2 above. And then underneath that, if I add in, I'll do 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. So this is different than the Fibonacci sequence. I'm not sure how to spell that. Maybe like that. And then this is Pascal's triangle. But one of the things that is related to them is that they do have that idea of you're adding two things. But in Pascal's triangle, what you're always adding are the two numbers that are directly above that honeycomb. So pause the video, finish out the rest of filling out the rest of the rows for Pascal's triangle, and then we'll compare. All right, so the completed first rows here, all the way down through that 13th row, is on the screen. One fast way for you to be able to compare to see if you got the right answers, just check your very last row. And if you didn't get the same values, then you can check above, pause the video, and see where you made your error. You may have just added incorrectly in one spot and carried the error all the way through along. So a couple things to notice that is helpful about Pascal's triangle. One is that we do have 1s all the way down on the edges. Something else that is nice to see is that we do have, along this diagonal, we do have all of the counting numbers. And same thing going the other direction. We have all the counting numbers right in here, which is helpful to see. Also, something else to kind of notice is that if we look at those along the green diagonals and the counting numbers, the number in that position is one less than the row number that you're in. So for example, right here is row 3, but the number in that counting number position is row 2. So like row 3, row 4, this is row 5, but the number in the counting position is a 4. So this right here is row 13, even though that counting number is a 12. So Pascal's triangle, it's pretty, it's interesting. There's a ton of applications for it. So we're going to look at one application that involves this triangle today. It also involves combinations. We'll come back to that. It has to do with binomial expansion. So a binomial, remember, has two terms. And when we expand it out, it's when we have the binomial. Wow, let's see if I can write. Uh-oh. Sorry, tech issue here. Let me pause the video. I think it's coming back. Okay, so binomial expansion, a binomial is when we have two terms. And when we expand it out is when we have these two terms taken to the power. And we multiply it out and combine like terms. Would you guys do this a lot when you do FOIL? So for example, you could expand this out as doing x plus 2 times x plus 2 and expand this out. We would get, if you FOIL or distribute x squared plus 2x. Now the middle terms will be the same. So we have a 2x and another 2x, which is a 4x plus 4. It is very helpful to recognize that this number is 2 times x. So it's twice the product of those two. And then this number would be the last value squared, as this is the first value squared. When you are squaring something and getting the resulting trinomial, that is always true. So, for example, on this one, we could, without actually expanding it out, get x squared minus 10x plus 25. Because the x squared comes from multiplying those first two. We have a minus 5x twice. So this would be twice the negative 5 and the x multiplied together. And then this right here would come from the last two terms multiplied together, or the negative 5 quantity squared. So see if you can use the pattern on number 3 to try to expand this out to the trinomial without actually having to write it out and going through all of the foiling. I mean, if you need to, you can, but why don't you try it and then pause the video while you try it and then restart it and compare. So the expansion of this one would be 16m squared plus 24mn plus 9n squared. If you are struggling at all with that, the 16m squared comes from that first term squared. Notice I'm squaring both the 4 and the m. In a similar fashion, the 9n squared comes from the 3n quantity squared. And then the middle term comes from 2 times the first term times the last term. And that's where the 24mn came from. Alternatively, you could FOIL this out by hand. So this one, we're going to expand out all of these different powers. And then we're going to make some conjectures. So we'll expand some of this together. As a reminder, to the power of 0, any non-zero value taken to the power of 0 is 1. X plus y to the first power, it's just times itself. X plus y quantity squared, if we use the power we've established, is x squared plus 2xy plus y squared. X plus y to the third power, we could find by taking the previous answer and multiplying them all by x and them all by y, and then adding that all up. So, in other words, we could multiply those together. Well, we've already got x plus y quantity squared. So then if I multiply that by another x plus y times what we just had, and I'll show you some work here so that we can hopefully eventually show less. I could first multiply all of those by x, which just changes the power of x for each of those terms. And then I can multiply them all by y. And then ultimately what I'd like to do is combine them all and combine the like terms. So this would end up being x cubed. And then x squared y, I do have two different terms with them, which combines to a 3x squared y. And then same thing with the xy squared. I have 2 and 1 of those like terms, so 3xy squared, and then plus y to the third. I'll erase all of the work for it just so that we have something simpler to look at. So now we're going to multiply that again by x plus y. So we'll distribute an x to all of those and a y and then combine like terms. So I'll pause the video. Why don't you try the next 2 rows and then we'll compare. I've got the 5th row completed here. This is actually my final answer. Below that would be the individual terms when I distributed in an x and then distributed in a y. A note about order of writing these in descending order. We do these in descending order of the x's, so that's why my terms are ordered in this fashion. And now I'm going to do the last row by multiplying my yellow portion here by x, and then by y, and then combining like terms, and I'll erase the other stuff just so that I am looking at something that's a little bit simpler to understand. I'll pause the video and restart it when you're ready. All right, so for row 5, here is what I got once I combine like terms. Below that has the individual terms before I combine like terms. So for the next part, we want you to look at these values, particularly look at maybe the coefficients of each of them, and look at the number of terms, look at the symmetry, and then compare them to what do you think kind of each row has. So compare it to the number of the row, and then kind of compare it to the row before it and after it. And then after you kind of verify that, write down like any ideas you have there. After you've done that, compare your expansion in Pascal's triangle and write down any observations. And then we're going to expand out. We'll do together the last bullet, but if you feel confident, go ahead and try it. So pause the video, write down your thoughts, and then restart it when you're ready. All right, so here are my thoughts. I noticed that the row number is one more than the degree or the highest power. So row 1 had a power of 0. Row 2 had a power of 1, and the highest power of x and y is 1. Row 3, the highest power is 2, and so forth. Now the number of terms, however, is the same as the row number, so which is 1 more than the power. So to the power of 3, for example, we had 4 terms. To the power of 5, we had 6 terms in the expansion. And then each row has symmetry for those coefficients. Kind of as you go left to the right, there's like the symmetry or mirror image here, kind of like a horizontal symmetry. If I compare the expansion to Pascal's triangle, I get the same number as the coefficients. Pascal's triangle looks like this. Sorry, see if I can write it. And notice that those are the exact same as the coefficients for each one. So we can use that then to expand out this. Now, something we need to keep in mind is that if I want the 10th power, what row would I need to be in? It's not the 10th row. Remember that the 5th power here was actually in the 6th row. So I would need to look at row 11 to help me with this expansion. So there's a hint. I'm going to pause the video and have you try that. See if you can use row 11 to expand this out. So what I did is I've got the coefficients from row 11 written down. And so how does this work then with the pattern of the powers? So let's maybe compare up above. Let's just look in at maybe row 4. So if the highest power is 4, notice how the powers of x will start at x to the 4th, and then they'll decline by 1 each time until there's no x's at the end term. Y's, on the other hand, would have a power of 4 for the last term because it's at the end, and then would decline as we move to the left and would not have any y's in the initial term. So what would happen here is the highest power for x that I should ever have is x to the power of 10. And then my powers of x should go down by 1 each time. I don't know if I gave myself enough room. You will see. Until at the very end, I should have no x's. My y's I should have no y's at the beginning, and I can add 1 each time until I have 10 y's at the end. And I shouldn't have any y's in the first term. Now, all of these are being added. If I had some subtractions in the problems, which we will explore shortly, this is so messy, please forgive me, then I would have potentially some minuses in the problem as I expanded this out. All right, so expanding the following binomials. If I'm using the power of 4, I would need to use row 5 for Pascal's triangle. So if I wanted to use row 5 for Pascal's triangle, keep in mind that row 5 has 5 digits in it, and it has the 4 along the diagonal. So that's 1, 4, 6, 4, and 1 as my coefficients. 1, 4, 6, 4, and 1. I'm going to give myself a little more space. Now I actually am going to have a little bit of work, one step of work before I get to my final answer. My first term, x, will start with the power of 4 and then decline until I have x to the power of 0 or no x's at the end. This time I don't have a y at the end, I have a 2. Well, that 2 needs to be taken to the power of 4 in the last term, 2 to the power of 3 as I move to the left, 2 to the power of 2, 2 to the power of 1, and then none of them here. And all of these will be added, but I do need to simplify and do some multiplying. My first term would then be x to the 4th, plus, this would be a 2 times 4. Those coefficients need to be multiplied together, those constants, to have a coefficient of 8 in front of the x cubed. For my next term, I would need to do 2 squared, which is 4, times 6, which is 24, x squared. For my fourth term, I'll do the power first. 2 cubed is 8, times 4 is 32. That's just the power of x. And then at the end, 2 to the 4th is 16. And so there's the expansion. So when would we potentially have a negative? Right here. When you think of the last term, you want to think of the first term as x and the last term as negative 2y. And so when you take that to various powers, you will have sometimes some positives and sometimes some negatives, and they will alternate as you take them to even or odd powers. So pause the video. I'm still using something similar. I'm still going to use Pascal's triangle. We will use row 6 on this one. So pause the video and give it a try. All right, so for number 5, my solution is up on the screen. Just kind of watch those signs. If you feel good with that, go on and try number 6. All right, so my expansion for number 6 is up on the screen. You just want to be really careful when you are taking some of these terms to the powers that you take both the constant and the variable to the power. So be careful with that. So for example, if I'm looking maybe at this term, the 3 needs to be taken to the third power, as well as the x. That's why it's x cubed here. So be careful with that. It's really easy to kind of miss that detail. So a binomial coefficient, when we are finding the coefficient, which would be the numbers that were from Pascal's triangle, these numbers right here. Well, we can find them by expanding out Pascal's triangle, but we could also find them by using combinations. So when would be useful to use the triangle is if you have to expand out the whole thing. But there are times where you maybe only have to find one of these terms, like maybe for number 6, you only want to find maybe the 5th term here. Then maybe you wouldn't want to use the whole triangle. Maybe that would be more work than it would be worth. Or maybe you're at a row that you're at like row 27 and you don't want to expand out that triangle all the way to that many rows. So here's kind of a formula that you can use. If you want to use this formula, you do need to memorize the formula here if you want to use it. So if you want to find the r plus 1 first term of the expansion a plus b to the power of n, here's how you would do it. This, you would do a combination on your calculator where n would be the power. So that first number would be the power that you're taking the whole expansion to. Here, this is r, and be careful. If you're finding, for example, the 6th term, this number down here is not 6. r plus 1, 6, this term would be considered 5 plus 1 would be the 6th term, and we'll talk more about that. And then what we would do is we would do, that would help us get that coefficient in the front. And then we would take this first term to the power of n minus r, and then the last term to the power of r. So let's do a couple examples of this so you can see it. Now, again, we could just use Pascal's triangle to help us with this, but I want to look at the expansion of this and find out the 5th term. So first of all, what the heck is r? If I want the 5th term, 5 is equal to r plus 1, which means r is 4. N, in this case, is the greatest power, which is 9. So I want to do a combination in the front of 9 combination 4. And then I want to take the first term, 2x, to the power of 9 minus 4. And then I want to take the last term, which is y, to the power of r, which is 4. So I'm going to use my calculator to find the combination of the value of 9 combination 4. Which ends up equaling 126. And then I will need to multiply that by 2 to the 5th, which is 32, x to the 5th, and then times y to the 4th. So I would definitely want to use my calculator to help with that. So I end up with 4,032 as the coefficient, x to the 5th, and y to the 4th. By the way, something that is true, that is helpful, is that these powers should always add up to the degree of 9. So pause the video. You try number 8. All right, my solution for number 8 is up on the screen. Because we're finding the 7th term, 7 is equal to r plus 1, so r is 6. N would always be the total degree power of 10. So I'll do 10 combination 6, which is 210. And then the first term would be taken to the power of the difference of n and r, which is why it's 4. And then the last term, including the negative, would be taken to the power of 6, which is r. Notice that these two powers should add up to a total power of 10. From there, I just had some calculations to do. My final answer was 13,440 x to the 4th, and that is the end of the notes for 10.5.